The year was 1917, and Harry Ferguson was watching a man die. Not literally, not in that moment, but the Irish engineer understood with perfect clarity that the farmer struggling in the muddy field before him was being killed by his own tractor, one back-breaking hour at a time. The machine, a Fordson Model F, bucked and lurched as its driver fought to control a mounted plow. The implement, hanging from rigid chains, had no relationship with the tractor beyond being dragged behind it. When the plow blade struck a buried rock, the entire rear end of the tractor reared upward like a startled horse. The farmer threw his weight forward, desperately trying to force the front wheels back to earth. One slip, one moment of lost control, and the machine would flip backwards, crushing him beneath a ton of cast iron and steel. Ferguson had seen it happen. Everyone had. Tractor fatalities were climbing at an alarming rate across Britain, Ireland, and North America. Between 1915 and 1920, backwards overturning killed hundreds of farmers and injured thousands more. The very machines promised to liberate agriculture from animal power were instead creating a new kind of danger, one that traditional farming had never encountered. But Ferguson wasn't watching that struggling farmer with horror, he was watching with calculation. Because Harry Ferguson understood something that no other engineer of his era had fully grasped. The problem wasn't the power. The problem was the connection. Every tractor of that period, whether built by Henry Ford, International Harvester, or any of the dozens of manufacturers flooding the market, treated implements as dead weight to be pulled. Plows, harrows, and cultivators hung from drawbars or chains, their depth controlled by manual adjustment, their relationship to the tractor mechanical rather than dynamic. When resistance increased, the implement simply transferred that force directly into the tractor's frame, trying to rotate the entire machine backward around its rear axle. The standard solution was to add weight. Manufacturers bolted cast iron weights to the front of tractors, trying to counterbalance the rotational force. Farmers were advised to fill their front tires with calcium chloride solution. Some even hung concrete blocks from the front axle. The tractors grew heavier, clumsier, more expensive to operate. Fuel consumption climbed, soil compaction worsened, the machines sank into soft ground, requiring more power to move, which required more weight, which required more power. It was an engineering spiral with no exit. Ferguson saw a different path. Born in 1884 near Belfast, Northern Ireland, Harry Ferguson possessed the kind of mind that couldn't leave a problem unsolved. He'd started his working life in his brother's garage, repairing automobiles and motorcycles when both were still exotic novelties. But Ferguson wasn't content with maintenance. He modified engines, redesigned chassis components, and in 1909 built his own airplane, the first to fly in Ireland. That aviation experience mattered more than anyone realized at the time. In the air, Ferguson had learned about control surfaces, about dynamic response, about systems that adjusted automatically to changing conditions. An airplane's elevator didn't just point the nose up or down through mechanical force. It created aerodynamic pressure that let the plane climb or descend smoothly, responding to airspeed and load. What if a plow could work the same way? The idea germinated through the late 1910s and early 1920s as Ferguson worked with various tractor designs. He experimented with different mounting systems, different geometries, different ways of connecting implement to power source. Traditional engineers approach the problem mechanically, make the connection stronger, the frame heavier, the linkage more rigid. Ferguson approached it dynamically. By 1925, he had developed his first workable prototype of what would eventually become the three-point hitch. The system used 3 connection points arranged in a triangle, 2 lower arms and 1 upper link, creating a rigid geometric structure that nonetheless allowed the implement to move in relation to the tractor. But geometry alone wasn't the innovation. Plenty of 3-point connections existed in engineering. Ferguson's breakthrough was making the system hydraulic and self-regulating. Here's how it worked and why it mattered. The implement, let's say a plow, attached to the tractor at 3 points forming a triangle. The 2 lower arms, mounted at the rear axle height, connected to the plow's frame at its lower corners. The single upper link, mounted higher on the tractor's drawbar area, connected to the plow's upper center. This triangular arrangement created a rigid geometric structure. Unlike chains or cables that flexed and allowed the implement to move independently, the three rigid links locked the plow into a fixed relationship with the tractor. But here's where Ferguson's genius emerged. The lower arms weren't truly fixed. They pivoted on the rear axle, allowing them to rise and fall. A hydraulic ram powered by a pump driven off the tractor's power takeoff could raise or lower these arms. When the operator pulled a lever, hydraulic pressure pushed the arms up, lifting the implement clear of the ground. Push the lever forward, and the arms lowered, setting the implement into working position. So far, this was clever, but not revolutionary. Other inventors had experimented with hydraulic implement lifts. Ferguson's true innovation was the draft control system. He added a spring-loaded sensing mechanism to the upper link. When the plow encountered resistance, hitting harder soil, striking a rock, or digging too deep, that resistance tried to push the plow forward relative to the tractor. The three-point geometry meant this forward push translated into compression on the upper link. Ferguson's spring mechanism detected this compression and automatically signaled the hydraulic system to raise the lower arms slightly, reducing the plow's working depth until resistance decreased to the preset level. The system was self-regulating. The implement automatically maintained constant draft force regardless of soil conditions. This created multiple cascading benefits that fundamentally changed tractor operation. First, it eliminated the overturning moment. When a traditional plow hit resistance, all that force transferred through the drawbar, trying to rotate the tractor backward. Ferguson's system instead transferred the force through the three-point geometry directly to the rear axle and downward into the ground. The harder the plow pulled, the more weight transferred to the rear wheels, increasing traction exactly when needed. The tractor couldn't flip backwards because the implement's resistance was actively pushing the rear wheels into the earth. Second, it provided automatic depth control. Traditional plows required constant operator attention, manually adjusting depth as soil conditions changed. Ferguson's system did this automatically through the draft control mechanism. Hit a hard spot, the plow lifted slightly. Enter softer soil, it lowered back down. The operator could focus on steering rather than constantly adjusting implement depth. Third, it turned the implement into functional ballast. When raised for transport, the three-point hitch lifted the implement's full weight onto the tractor's frame, directly over the rear axle. A 500-pound plow became 500 pounds of perfectly positioned ballast, improving traction and stability without requiring expensive cast iron weights. Lower the implement into work, and that weight transferred through the cutting edge into the soil, exactly where it provided the most benefit. Fourth, it enabled the use of lighter tractors. Because the system transferred weight dynamically rather than requiring massive front-end ballast, manufacturers could build smaller, lighter, more efficient machines. A 2,000-pound Ferguson tractor with a mounted plow could outwork a 4,000-pound conventional tractor pulling the same plow on a drawbar. Ferguson demonstrated these advantages throughout the late 1920s and early 1930s, but selling the idea was harder than developing it. Established tractor manufacturers looked at Ferguson's system and saw expensive complexity solving a problem they didn't acknowledge. International Harvester, John Deere, Massey Harris, these companies had invested millions in existing designs. Their engineering departments were staffed with men who'd spent decades perfecting drawbar tractor design. Ferguson's claim that the entire industry was fundamentally wrong didn't win friends. He needed a partner with vision, resources, and willingness to challenge convention. In 1938, Harry Ferguson found that partner in Henry Ford.
The famous handshake happened on October 28, 1938, in a barn at Dearborn, Michigan. No lawyers, no written contracts, no corporate oversight. Just two men, Harry Ferguson and Henry Ford, agreeing to revolutionize agriculture based on mutual trust and a shared belief that farming needed better tools. Ford had watched Ferguson demonstrate his tractor system that afternoon, plowing a test field behind Ford's headquarters. The performance impressed him. More importantly, Ferguson's explanation of the hydraulic draft control system aligned perfectly with Ford's own engineering philosophy. Make things simpler, lighter, more efficient. Strip away unnecessary weight and complexity. Let intelligent design replace brute force. Ford agreed on the spot to manufacture tractors incorporating Ferguson's system. Ferguson would design the machine, Ford would build it, and they'd share the profits. No patents would be filed in Ford's name. The system would remain Ferguson's intellectual property. Ford would pay a royalty on every tractor sold. They shook hands. The deal was done. Or so Ferguson believed. The Ford Ferguson 9N entered production in 1939, and it was immediately obvious that something revolutionary had arrived. The machine weighed just 2,340 pounds, less than half the weight of comparable tractors. It sold for $585, undercutting competitors by 30% or more, and it could outwork machines twice its size. The three-point hitch had evolved considerably from Ferguson's 1920s prototypes. The production system used a more sophisticated hydraulic circuit with positive flow control. The draft sensing mechanism had been refined to provide smoother, more consistent response. Most importantly, Ford and Ferguson's engineers had standardized the mounting points, creating what would become known as Category 1 geometry, a set of precise dimensions for the lower arm ball ends, the upper link connection point, and the check chains that prevented lateral movement. This standardization mattered enormously. It meant any implement built to Ferguson specifications would fit any Ferguson system tractor. Farmers could buy a plow from one manufacturer, a cultivator from another, a mower from a third, and all would attach and work identically. The three-point hitch wasn't just a connection system, it was an interface standard that would eventually spread across the entire agricultural equipment industry. The hydraulic circuit on the 9N was elegantly simple. A pump, driven by a gear train off the engine's timing case, drew oil from the transmission housing and delivered it to a control valve mounted within easy reach of the operator's seat. The valve had three positions: raise, neutral, and lower. Move the lever back to raise, and the pump's full output flowed to a single hydraulic cylinder mounted on the right side of the rear axle housing. The cylinder's rod connected directly to the right lower arm lift through a simple pin joint. The left lower arm connected to the right arm through a lift rod, essentially a horizontal link that ensured both arms moved in unison. When the cylinder extended, it pushed the right arm up, which pulled the left arm up through the connecting rod. When the cylinder retracted, both arms lowered together. This single-cylinder design was a masterstroke of cost reduction. Competitors building hydraulic implement lifts used dual cylinders, one for each arm, requiring more complex plumbing and doubling the number of potential failure points. Ferguson proved that proper geometry made the second cylinder unnecessary. The lateral connecting rod kept everything synchronized, while the three-point hitch geometry prevented the implement from twisting or binding. The draft control mechanism added another layer of sophistication. Inside the control valve body, a spring-loaded cam rode against a lever connected to the upper link. When draft resistance increased, compression on the upper link rotated this internal lever, which moved the valve spool slightly toward the raise position. The pump immediately sent a measured amount of oil to the lift cylinder, raising the implement just enough to reduce resistance back to the preset level. The system reacted almost instantly, typically within a fraction of a second, maintaining remarkably consistent draft force. Farmers who'd spent decades fighting with manually adjusted implements found the experience almost magical. Drive into the field, lower the plow to start depth, set the draft control lever, and focus entirely on steering. The tractor handled everything else. Hit a rock, and the plow would lift just enough to clear it before dropping back to working depth. Transition from loose soil to packed clay, and the depth automatically adjusted to maintain steady pulling resistance. The system's behavior under load revealed Ferguson's deep understanding of weight transfer physics. As draft resistance increased, before the draft control responded, that resistance pushed forward through the three rigid links, creating a downward force on the tractor's rear axle. The lower hitch points were behind the rear axle centerline. So forward force from the implement translated to downward pressure at the axle. The harder the plow pulled, the more weight pressed onto the rear tires. This explains why the 9N, despite its modest weight, could pull implements that would cause heavier conventional tractors to spin their wheels helplessly. A 4,000-pound Alice of Challenger WC pulling a two-bottom plow on a drawbar had its full 4,000 pounds distributed across front and rear axles according to the machine's static weight distribution, roughly 1,600 pounds on the rear wheels. That 1,600 pounds determined maximum pulling force before the tires lost traction. The 2,340-pound Ford Ferguson 9N pulling the same two-bottom plow through the three-point hitch might have only 1,000 pounds static rear axle weight. But as soon as the plow engaged the soil, draft resistance transferred perhaps 800 additional pounds onto the rear axle through the hitch geometry. Now the rear tires had 1,800 pounds pressing them into the earth, more than the heavier Alice of Challenger, despite the Ford weighing nearly half as much. The front wheels lightened correspondingly, sometimes lifting clear of the ground during heavy pulling. This worried observers who didn't understand the physics. Surely a tractor with its front wheels in the air was about to flip backwards. But it couldn't. The three-point geometry made backward overturning physically impossible. The lower hitch points were below the rear axle centerline and behind it. Any rotational force trying to lift the front of the tractor would have to compress the lower arms, literally crush solid steel links, before the rotation could continue far enough to reach the tipping point. The implement itself acted as a strut, bracing the tractor against backward rotation. Ferguson demonstrated this repeatedly, sometimes to dramatic effect. He'd set a plow to excessive depth, deliberately creating far more resistance than the tractor should handle. Then engage the clutch. The front wheels would rise. Observers would gasp. The tractor would simply sit there, front wheels hanging in the air, rear wheels churning steadily forward, plow biting deep, absolutely stable and completely safe. Try the same demonstration with a drawbar tractor, and the machine would immediately begin rotating backward toward a catastrophic flip. The 9N's transmission and final drive were equally well conceived, designed specifically to work with the three-point hitch's characteristics. Ford's engineers used a sliding gear transmission with 3 forward speeds and 1 reverse, giving ratios of approximately 2.75 miles per hour, 4.75 miles per hour, and 7.75 miles per hour in the forward gears. These speeds were carefully chosen to match typical implement operations: cultivation in first gear, plowing in second, transport in third. The final drive used a spur gear reduction housed in cast iron cases bolted to either side of the rear axle. This design, called a unit frame construction, integrated the transmission, differential, and final drives into one rigid structure that served as the tractor's main frame. The engine and front axle bolted directly to this central unit. The approach saved weight while providing a rigid mounting surface for the three-point hitch's lower arm lifts. Between 1939 and 1947, Ford manufactured over 300,000 Ford Ferguson 9N and 2N tractors. The 2N was a wartime version with steel wheels and magneto ignition due to material shortages. These machines spread across American farms, proving the three-point hitch's superiority in thousands of real-world operations.
Ferguson himself focused on implement design. His company, Harry Ferguson, Inc., developed a complete line of mounted equipment: plows, cultivators, mowers, hay rakes, planters, even a side-mounted sickle bar mower that used a second hydraulic circuit. Each implement was engineered to take maximum advantage of the three-point hitch's characteristics: lightweight, compact design, optimized for mounted operation rather than trailing. Other manufacturers began designing Ferguson-compatible implements. Sherman Brothers, Dearborn Motors, and dozens of smaller companies build equipment to Ferguson's system specifications. The standardized hitch geometry meant perfect interchangeability. By the mid-1940s, farmers could choose from hundreds of different implements, all guaranteed to fit and work with any Ferguson system tractor. But storm clouds were gathering. Henry Ford's health was declining. His son, Edsel, had died in 1943, leaving Henry Ford III, Edsel's son, to gradually assume control of the company. The younger Ford had little patience for informal handshake agreements. He wanted formal contracts, clear terms, and most importantly, he wanted to stop paying Ferguson royalties on every tractor sold. In 1947, without warning, Ford Motor Company announced it would cease production of the Ford Ferguson tractor. The company would instead build a new model, the Ford 8N, that featured a 3-point hitch but incorporated enough changes to arguably avoid Ferguson's patents. Ford claimed the new design was sufficiently different to avoid royalty obligations. Ferguson sued immediately, filing what would become one of the largest and most complex patent lawsuits in industrial history. Ferguson versus Ford Motor Company went to trial in 1951. Ferguson's legal team argued that Ford had stolen his inventions, violated their handshake agreement, and deliberately designed the 8N to infringe his patents while claiming innovation. They demanded $340 million, roughly $3.8 billion in today's dollars. Ford's attorneys countered that the handshake agreement had been terminable at will, that Ford had substantially improved Ferguson's earlier designs, and the 8N's hitch was sufficiently different to constitute original engineering. The trial lasted months. Engineers testified about linkage geometry, hydraulic circuit design, and draft control mechanisms. Lawyers argued about patent claim language, prior art, and the enforceability of oral agreements. Ferguson himself took the stand, explaining his inventions in meticulous detail. The court ultimately ruled partially in Ferguson's favor. Yes, Ford had infringed certain patents. Yes, damages were owed, but no, $340 million was excessive. The final settlement, reached in 1952, awarded Ferguson approximately $9.25 million. Ferguson had won legally, but he'd lost his manufacturing partner. Rather than crushing him, the Ford split pushed Ferguson towards an even more significant partnership, one that would spread the 3-point hitch across the entire world. In 1953, Harry Ferguson Inc. merged with the Canadian farm equipment manufacturer Massey Harris Ferguson, creating Massey Harris Ferguson, later shortened to Massey Ferguson. The combined company became the third largest agricultural equipment manufacturer in the world, with factories on 3 continents and a product line that would make Ferguson's system the global standard. The engineers at Massey Harris looked at Ferguson's patents and saw an opportunity that went far beyond tractors. Ferguson's 3-point hitch wasn't just a mounting system, it was a universal interface, a standardized connection that could link any power source to any implement through a consistent geometric relationship. The principles worked regardless of tractor size, implement weight, or application. This realization drove Massey Ferguson's engineering expansion through the 1950s and 1960s. The company developed multiple hitch categories to accommodate different machine sizes and implement weights. Category 1, Ferguson's original specification, served tractors in the 20 to 45 horsepower range, the core agricultural market. Category 2, with larger diameter pins and heavier linkage components, handled 40 to 100 horsepower tractors pulling heavier implements. Category 3, introduced later, accommodated industrial tractors and agricultural machines above 80 horsepower. Each category maintained Ferguson's essential geometry, the triangular arrangement, the draft sensing through the upper link, and the hydraulic control system, but scaled the physical components appropriately. A Category 2 lower link pin measured 7/8 inch versus Category 1's 3/4 inch, providing the extra strength needed for heavier implements without changing the fundamental operating principles. The genius of this categorization was interoperability within size classes. Every Category 1 tractor from any manufacturer, Massey Ferguson, Ford, International Harvester, John Deere, Alice Chalmers, used identical pin sizes and spacing. An implement built to Category 1 specifications would fit any Category 1 tractor regardless of who manufactured it. The industry had inadvertently standardized on Ferguson's geometry, making the 3-point hitch the agricultural equivalent of standardized railroad track gauge. This standardization accelerated implement innovation dramatically. Manufacturers could design equipment knowing it would fit thousands of different tractors across dozens of brands. Development costs dropped, market opportunities expanded. A small company in Iowa building specialized potato planters could sell to any farmer owning any compatible tractor, rather than needing to design separate versions for Ford, John Deere, and International Harvester mounting systems. The implement variety exploded accordingly. By the early 1960s, manufacturers offered 3-point mounted versions of nearly every agricultural tool: multi-bottom plows that could break 4 furrows simultaneously, rotary tillers that pulverized soil with spinning tins, post-hole diggers using tractor hydraulics to power an auger, backhoes that turned farm tractors into excavators, front-end loaders with hydraulic bucket control, mowers that could cut and condition hay in a single pass, balers that formed compressed hay packages, manure spreaders, fertilizer applicators, and grain drills. Industrial applications followed agricultural ones. Construction companies discovered that a farm tractor with a 3-point mounted backhoe cost a fraction of a dedicated excavator while providing nearly equivalent digging capability for light work. Municipalities used 3-point mounted snowplows, sweepers, and mowers to maintain roads and parks. The forestry industry adopted 3-point mounted log splitters and chippers. But Ferguson's system offered more than just versatility. The hydraulic control and draft sensing created entirely new operational possibilities. Consider a rotary tiller, an implement with spinning tins that pulverize soil. Traditional tiller design used ground wheels to control depth. As the wheels rolled along the surface, they regulated how deep the tins could penetrate. This worked, but it created problems. In soft soil, the wheels sank, allowing the tins to dig too deep and bog down the tractor. In hard soil, the wheels prevented the tins from penetrating adequately. A 3-point mounted tiller eliminated the wheels entirely. The hydraulic system controlled depth, adjusting constantly through Ferguson's draft sensing mechanism. Hit a soft spot and the tiller lifted slightly to prevent bogging. Enter hard ground, and hydraulic pressure forced the tins to bite deeper. The operator set desired resistance, and the system automatically found the depth that produced that resistance in whatever soil conditions existed. This automatic adjustment meant more consistent results with less operator skill required. A novice could achieve tillage quality that previously demanded years of experience and constant attention. The post-hole digger provided an even more dramatic example. This implement used a vertical auger, essentially a large drill bit, to bore holes for fence posts. Traditional post-hole diggers were separate machines with their own engines, requiring 2 workers to operate and transport them around the farm. The 3-point mounted version replaced the separate machine entirely. The auger mounted vertically on a frame attached to the tractor's 3-point hitch. A power takeoff shaft running from the tractor's transmission to the auger provided rotation. The hydraulic system provided downward force, the operator controlling how much pressure pushed the spinning auger into the ground. Drill into soil, and the operator felt resistance through the draft control. Applying excessive downward pressure would stall the auger. Insufficient pressure allowed the bit to spin without cutting. Ferguson's hydraulic system let the operator modulate pressure precisely,
feeling through the control lever exactly how much force the auger needed. Hit a rock or root, and that sudden resistance fed back through the draft control immediately. The operator could stop forward pressure, back the auger out, clear the obstruction, and resume boring, all without dismounting from the tractor seat. One person could now dig dozens of post holes in the time it took previously 2 people with a separate machine to dig a handful. The front-end loader represented perhaps the most transformative 3-point application. Agricultural tractors had traditionally been pulling machines, using their power to drag implements through the soil. Adding a loader converted them into lifting machines, capable of moving materials vertically rather than just horizontally.
Early tractor-mounted loaders used mechanical linkages, operated through cables or manual levers. The operator would engage a clutch to transfer power from the engine to a system of pulleys and cables that lifted the loader bucket. Lowering required releasing the clutch and allowing gravity to drop the load. These mechanical systems were slow, imprecise, and offered no modulation. The bucket went up at full speed or not at all. 3-point mounted loaders, which attached the tractor's rear hitch while extending forward alongside the engine, initially used the tractor's rear hydraulics. But this proved awkward. Operating a front-mounted implement with rear-mounted controls required the operator to essentially work backward. Ferguson's solution was to develop auxiliary hydraulic circuits. These additional circuits tapped the same hydraulic pump, but directed flow to separate control valves for front-mounted implements. An operator could control rear-mounted implements with one lever and front-mounted equipment with another, each responding independently. Later designs incorporated load sensing into the loader hydraulic circuit itself. When the bucket lifted a heavy load, pressure in the hydraulic system increased proportionally. Ferguson's engineers designed control valves that responded to this pressure, automatically adjusting flow to maintain smooth lifting speed regardless of load weight. Pick up an empty bucket and it lifted quickly. Fill the bucket with half a ton of grain, and the hydraulic system compensated automatically, maintaining steady lifting speed. This load compensation seems minor until you've operated a loader without it. Uncompensated systems lift empty buckets so rapidly they slam into the mechanical stops with bone-jarring force, while heavy loads creep upward at glacial speed. Load sensing made the loader feel natural, responsive, predictable, essential qualities when maneuvering around livestock, buildings, and people. The backhoe attachment demonstrated 3-point hitch versatility at its peak. This implement transformed a standard farm tractor into an excavator, providing digging capability that previously required a dedicated construction machine costing 5 to 10 times more. The backhoe assembly consisted of 2 main components: a subframe that attached to the tractor's 3-point hitch, and the articulated digging arm with bucket that mounted to the subframe. The subframe included stabilizers, hydraulically operated legs that lowered to the ground on either side of the tractor, lifting the rear wheels clear and providing a stable platform for digging operations. The arm had 3 hydraulic cylinders controlling boom height, stick angle, and bucket curl. These cylinders received hydraulic power through an auxiliary pump mounted on the tractor, driven by the power takeoff shaft. The operator controlled all 3 functions through a separate valve bank, typically mounted on a pedestal beside the tractor seat. Operating a tractor-mounted backhoe required learning entirely new control inputs. Unlike a farm implement that worked automatically, the backhoe demanded continuous manual control. The operator had to coordinate boom lift, stick curl, and bucket angle simultaneously to follow a smooth digging arc, while also controlling the tractor's steering and sometimes its forward or reverse motion. Despite the learning curve, the economic benefits were overwhelming. A farmer could excavate foundation trenches, dig drainage ditches, install water lines, and clear stumps using equipment that also plowed fields and mowed hay. The tractor earned its keep year-round, rather than sitting idle between seasonal agricultural tasks. Massey Ferguson productized these applications throughout the 1950s and 1960s, developing complete implement lines that showcased 3-point hitch capabilities.
But other manufacturers were watching closely, recognizing that Ferguson's system had become the de facto industry standard. John Deere, historically committed to their own proprietary hitch designs, began offering three-point hitches on their tractors in the late 1950s. International Harvester followed. Alice Chalmers, Case, Minneapolis Moline, every major manufacturer eventually adopted Ferguson's geometry and control principles, though each claimed their implementation was somehow superior or different. The reality was that Ferguson's patents, combined with the handshake agreement lawsuit's publicity, had made the three-point hitch legally hazardous to ignore but economically essential to adopt. Manufacturers needed to offer compatible implements to remain competitive, which required offering compatible tractors. The system had achieved critical mass, becoming a network effect from which no manufacturer could afford to disconnect. Ford, ironically, became one of the system's strongest proponents. The 8N that had sparked the Ferguson lawsuit remained in production until 1952, selling over 500,000 units. Its successors, the NAA, the 600-800 series, the 1000 series, all featured three-point hitches following Ferguson's specifications. Ford had fought Ferguson in court, but adopted his invention in practice. By 1960, virtually every new tractor manufactured in North America and Europe included a three-point hitch as standard equipment. The system had conquered agriculture in barely 2 decades, spreading from Harry Ferguson's workshop to worldwide adoption faster than almost any agricultural innovation in history. But the system's influence was still expanding. Engineers were discovering that Ferguson's principles applied far beyond agriculture.
The Japanese engineers at Kubota studied Ferguson's patents with particular interest in 1960. Japan's agricultural landscape bore little resemblance to the sprawling North American farms Ferguson had originally targeted. The average Japanese farm measured less than 3 acres, divided into even smaller rice paddies separated by raised earthen berms. Farmers worked these paddies by hand or with small, underpowered walking tractors, basically motorized tillers with handlebar steering. Kubota's challenge was adapting Ferguson's system to machines 1/10 the size of American farm tractors. Could the three-point hitch work on a 10-horsepower machine intended for paddies that might measure only 50 feet square? The answer required rethinking scale while preserving principles. Kubota's engineers created a subcompact category they called Limited Category 1, using 5/8-inch diameter lower link pins instead of the standard 3/4 inch. The hitch geometry remained proportionally identical to Ferguson's original, the same triangular relationship, the same pivot points, the same basic control system, but every component shrank to match the reduced machine size and power output. The hydraulic system proved particularly challenging. American tractors used hydraulic pumps producing 5 to 8 gallons per minute at 2,000 psi, more than enough flow to rapidly lift heavy implements. A 10-horsepower engine couldn't spare the power to drive such a pump without sacrificing performance. Kubota's solution was a tiny gear pump producing less than 2 gallons per minute at 1,500 psi, barely a quarter of American tractor output. This required redesigning the entire hydraulic circuit for efficiency. The lift cylinder's bore shrank to 1.5-inch diameter, reducing the volume of oil needed for each lift cycle. The control valve used tighter tolerances to minimize internal leakage. The draft control sensing mechanism gained higher spring rates to trigger with the lighter draft loads a small tractor would encounter. The resulting system lifted implements slower than its American counterparts, taking perhaps 5 seconds to fully raise a small plow versus 2 seconds on a Ford. But it worked, providing the same automatic draft control and weight transfer benefits that made Ferguson's system revolutionary, scaled to paddies instead of prairies. Other Japanese manufacturers followed Kubota's lead. Yanmar, Iseki, and Mitsubishi all developed compact three-point hitches for their small tractors. Within a decade, the system had become standard on Japanese agricultural equipment despite the dramatic difference in scale from Ferguson's original application. European manufacturers discovered different challenges. Agricultural practices varied widely across the continent. Small vineyards in France, large grain farms in Ukraine, mixed crop operations in Germany, pastoral grazing in Ireland. Could a single Hitch standard serve such diverse requirements? The answer came through categorization and optional features. A French vineyard tractor might use Category 1 geometry but add narrow track width for maneuvering between vine rows. A German grain farm tractor might use Category 2 for heavier implements but delete draft control in favor of simpler position control, maintaining fixed implement height rather than sensing draft load. An Irish dairy tractor might add a front 3-point hitch for loader mounting while retaining a standard rear hitch for mowing. Each variation preserved Ferguson's core geometry while adapting auxiliary features to local requirements. The standardized pin sizes and spacing meant implements remained interchangeable despite these regional modifications. Communist bloc countries presented a different situation entirely. The Soviet agricultural policy emphasized massive mechanization using giant tractors and enormous implements. The Soviet-manufactured Belarus tractors used 3-point hitches but scaled to Category 3 dimensions that would have been considered industrial equipment in the West. A Belarus 80-horsepower tractor with Category 3 hitch could lift implements weighing over 2,000 pounds, compared to the 600-pound capacity of Ferguson's original Category 1 design. The Soviets also developed proprietary variations supposedly offering improvements over Western designs. The automatic coupling system allowed implements to be attached without the operator leaving the seat. The tractor simply backed into alignment and mechanical latches engaged automatically when hydraulics lifted the hitch. This innovation predated John Deere's similar quick coupler system by several years, though the Soviet implementation proved less reliable due to precision manufacturing limitations. Eastern European manufacturers like Zetor in Czechoslovakia and Ursus in Poland largely followed Western standards, their equipment being sold internationally and needing to maintain implement compatibility. By the 1970s, 3-point hitch geometry had become genuinely universal, transcending political and economic systems to establish a shared interface standard spanning the entire industrialized world. The construction industry's adoption followed a different trajectory. While agricultural tractors converted to Ferguson's system in the 1950s, construction equipment manufacturers resisted through the 1960s, preferring purpose-built machines over adaptable farm tractors.
But economics won eventually. A farmer who already owned a tractor for agricultural work represented a potential customer for construction attachments if those attachments could use the existing 3-point mounting system. Implement manufacturers began offering construction-grade equipment built to 3-point specifications: heavy-duty backhoes with digging depths exceeding 10 feet, front loaders with buckets holding half a cubic yard, box scrapers for road grading, landscape rakes, trenchers, and augers. The 3-point hitch's weight transfer characteristic proved particularly valuable in construction applications. When a backhoe dug into resistant material, draft load tried to lift the rear of the tractor. The 3-point geometry converted this lifting force into downward pressure at the rear axle, increasing stability exactly when the machine was least stable. Without this characteristic, tractor-mounted backhoes would have been dangerous. The digging force would have tried to flip the machine backward. Forestry applications pushed the system's limits. Logging operations needed to move extremely heavy loads, tree trunks weighing several tons. Could a 3-point hitch handle such weights? The answer required distinguishing between implement weight and draft load. Ferguson's system was designed for draft control, sensing and reacting to pulling or digging resistance. Lifting static implement weight was a separate challenge, limited by the hydraulic cylinder's force and the linkage geometry's mechanical advantage. A standard Category 1 hitch could lift about 600 pounds of static implement weight,
This was adequate for an agricultural plow, but insufficient for a loaded log grapple. Category 2 increased capacity to roughly 1,200 pounds. Category 3 reached 2,500 pounds or more, depending on specific tractor design. But even Category 3 proved inadequate for the heaviest forestry work. Manufacturers developed specialized forestry hitches using larger cylinders, reinforced linkages, and modified geometry. These hitches abandoned draft control entirely, focusing purely on lifting capacity. Some designs used dual cylinders, one on each lower arm, to distribute load more evenly. These specialized variations demonstrated both the system's flexibility and its limits. Ferguson's core geometry could be adapted to almost any application, but extreme requirements eventually demanded departures from the original design principles. The hydraulic circuit's evolution through the 1960s and 1970s showcased continuous refinement. Early systems used simple open-center circuits where the pump ran constantly, circulating oil through the control valve and back to the reservoir when no implement motion was needed. This wasted energy. The pump consumed several horsepower just circulating oil. Closed center circuits addressed this inefficiency. These systems used accumulator tanks, pressurized oil reservoirs that stored hydraulic fluid under pressure when not in use. The pump only ran when accumulator pressure dropped below a threshold, reducing parasitic power loss. When the operator activated the hitch, stored pressure from the accumulator provided immediate response while the pump ramped up to replenish the system. Load sensing circuits refined efficiency further. These systems varied pump output based on actual hydraulic demand. Lifting a light implement required less flow, so the pump's displacement reduced automatically. Lifting a heavy implement demanded maximum flow, and the pump responded by increasing output. This variable flow saved fuel while maintaining responsive control. Electronic control entered the picture in the 1980s. Early implementations simply replaced mechanical linkages with electronic sensors and electrically actuated valves, but the fundamental operating principle remained Ferguson's draft sensing concept. A strain gauge on the upper link detected compression, sending a signal to an electronic controller that modulated hydraulic valve position. Later systems added sophistication. Digital controls allowed storing multiple implement settings in memory. A farmer could recall the exact depth and draft settings for the plow versus the cultivator with the push of a button. Automatic lift at end-of-row features detected when the tractor turned at field boundaries and automatically raised the implement, lowering it again when the tractor straightened for the next pass. These electronic enhancements preserve Ferguson's core invention, the automatic relationship between draft sensing and implement depth control. The sensors changed from mechanical springs to electronic strain gauges. The valve actuation changed from mechanical linkages to electric solenoids, but the underlying principle remains identical to what Ferguson demonstrated in that muddy Irish field in the 1920s. The implement attachment mechanism saw similar evolution. Ferguson's original system required manually inserting clevis pins through the ball ends of the lower arms, then connecting the upper link and adjusting its length with a turnbuckle. This process took several minutes and required getting down from the tractor seat. John Deere's quick coupler system, introduced in the 1960s, used spring-loaded latches that engaged automatically when the tractor backed into position near an implement. The operator would raise the hitch, the latches would grab the implement's mounting frame, and attachment was complete. Disconnection required pulling a release lever. ASAE, American Society of Agricultural Engineers, standardized this quick coupling interface in the 1970s, creating universal specifications that allowed any quick-attach implement to work with any compatible tractor. The standardization extended Ferguson's interface concept from geometry to the coupling mechanism itself. Modern quick-attach systems add hydraulic connections. The implement mounting frame includes hydraulic couplers that mate automatically when the hitch raises into attachment position. A single hydraulic motion connects both the mechanical linkage and the hydraulic circuit, allowing implements with hydraulic cylinders like loaders or grapplers to attach in seconds without manual connection of hydraulic hoses. Throughout all these refinements, Ferguson's geometric relationship remains unchanged. The triangular arrangement, the lower arms pivoting at the rear axle, the upper link sensing draft, these fundamental elements persist because they solve physical problems that don't change with technology: weight transfer, automatic depth control, and stable implement attachment.
Harry Ferguson died in 1960, never seeing how completely his invention would dominate global agriculture. By the time of his death, three-point hitches were already standard equipment on the majority of tractors manufactured worldwide. But the system's spread was still accelerating. Through the 1960s and 1970s, it penetrated markets Ferguson himself had never imagined. India's Green Revolution depended partly on three-point hitch technology. The country's shift from hand cultivation to mechanized farming required tractors simple enough for minimally trained operators to use effectively. Ferguson's automatic draft control meant a farmer transitioning from ox-drawn plow to tractor could achieve consistent results without years of learning manual depth adjustment skills. Manufacturers like Mahindra and Escorts built tractors under license from international companies, all incorporating three-point hitches. By 1980, India manufactured over 100,000 tractors annually, virtually all equipped with Ferguson's system. The country's wheat and rice production tripled between 1960 and 1980, fed partly by mechanization that three-point hitch technology enabled. China followed a similar pattern later. The country's agricultural mechanization accelerated rapidly after economic reforms in the 1980s opened markets to Western technology. State-owned manufacturers like YTO, First Tractor Factory, and private companies like Foton produced tractors incorporating three-point hitches based on European designs. By 2000, China manufactured over 200,000 tractors annually. By 2020, that number exceeded 500,000 units, more tractors than the United States, Europe, and Japan combined. Africa's adoption came more slowly, complicated by infrastructure limitations, parts availability challenges, and the economics of smallholder farming. But even here, three-point hitch technology spread through the simplest possible implementation. Chinese manufactured compact tractors sold at a fraction of Western prices. These machines often lacked sophisticated hydraulic controls or electronic features, but they retained Ferguson's basic geometry and manual draft sensing, providing the core benefits at the lowest possible cost. The system's influence extended beyond agriculture into unexpected applications. Garden tractors, essentially miniaturized farm tractors for residential use, adopted three-point hitches in the 1960s. Manufacturers like Wheelhorse, Simplicity, and Cub Cadet built machines with 10 to 20 horsepower engines that used subcompact three-point hitches compatible with miniature versions of agricultural implements. Homeowners could attach small plows, cultivators, even single-row corn planters to machines that otherwise simply mowed lawns. The industrial forklift industry discovered three-point principles applied to material handling. While forklifts don't use literal three-point hitches, their load carriage systems employ similar geometry. The load attaches at multiple points in a rigid triangular relationship that transfers weight towards the drive wheels as lifting height increases. This weight transfer prevents the forklift from tipping forward under load, exactly as Ferguson's system prevents tractors from flipping backwards while plowing. Zero-turn lawnmowers, introduced in the 1960s and refined through the following decades, also borrowed three-point concepts. These machines attach mower decks through systems that automatically adjust cutting height while maintaining level attitude relative to the ground. The geometry mirrors Ferguson's approach, sensing ground resistance through the cutting deck,
automatically lifting over obstacles, transferring weight to drive wheels during heavy cutting. Even military applications emerged. Combat engineering vehicles used three-point hitches to mount mine plows, earth-moving blades, and other battlefield preparation equipment. The weight transfer characteristic provided stability during aggressive operations, while quick attach systems allowed rapid mission reconfiguration. But perhaps the most significant evolution occurred in precision agriculture. Modern tractors incorporate GPS guidance, variable rate application, and automated control systems that make autonomous operation increasingly practical. How does Ferguson's 1920s mechanical invention integrate with 21st century digital technology? Surprisingly seamlessly. The three-point hitch's mechanical geometry remains unchanged, but modern tractors add layers of electronic control that automate what Ferguson's system required an operator to manage manually. Current high-end agricultural tractors use implement isobus systems, a standardized electronic communication protocol that allows tractors and implements to exchange data. When an implement attaches, it transmits its identity, operating parameters, and control requirements to the tractor's computer. The tractor automatically loads the appropriate control settings, configures its hydraulic system to match implement needs, and presents customized controls on the operator's display screen. Draft sensing remains fundamental, but now uses multiple load cells, providing continuous analog measurement rather than Ferguson's binary threshold spring. The tractor's computer monitors draft load hundreds of times per second, adjusting implement depth through proportional hydraulic control rather than simple on-off response.
GPS integration allows the system to anticipate rather than merely react. As the tractor approaches a field boundary, the GPS system knows the implement should lift. It commands the hitch to raise before the operator initiates the turn, saving seconds on every pass and reducing operator workload. Automatic section control extends this further. When planting or spraying, the implement can automatically deactivate sections that would overlap previously covered ground, eliminating waste. The three-point hitch's hydraulic system provides the control interface, raising and lowering individual sections or adjusting their operating parameters based on GPS position data. These sophisticated controls amplify Ferguson's core innovation rather than replacing it. The geometric relationship still transfers implement resistance into downward force at the rear axle. The triangular linkage still prevents backward overturning. The hydraulic system still provides automatic depth control. Modern electronics simply make these characteristics more precise, more consistent, and less dependent on operator skill. The standardization Ferguson created has proven remarkably durable. Category specifications defined in the 1950s remain in use today. A Category 1 implement manufactured in 2024 will fit a Ford N9 tractor from 1939, assuming someone updated the antique tractor's hydraulics to modern flow rates. The mechanical interface hasn't changed in 85 years. This longevity contrasts sharply with most agricultural technology. Harvest equipment from the 1950s is completely incompatible with modern grain handling systems. Planting equipment has undergone multiple revolutionary changes. Irrigation technology bears no resemblance to its mid-century predecessors. But three-point hitch geometry remains constant because it solves problems rooted in physics rather than technology. Gravity still pulls downward. Leverage still requires fixed pivot points. Weight transfer still follows mechanical advantage rules. These physical laws don't change, so Ferguson's geometry optimized around them remains optimal. The economic impact of this standardization is difficult to overstate. Implement manufacturers can design a single product that fits the global installed base of compatible tractors,
hundreds of millions of machines spanning decades of production. Development costs spread across this enormous market enable specialized equipment that would be economically impossible without standardization. A manufacturer building automated lettuce harvesters, for instance, can design around standard three-point hitch interfaces, knowing their product will fit thousands of potential customer tractors. Without that standardization, they'd need to design separate mounting systems for each tractor brand, multiplying engineering costs and inventory complexity to the point where the specialized implement likely wouldn't exist at all. This phenomenon, standardization enabling innovation in complementary products, extends far beyond agriculture. The USB connector standard enabled the explosion of computer peripherals. Railroad track gauge standardization allowed railcar manufacturers to build specialized equipment for niche applications. Shipping container standardization revolutionized global trade. Ferguson's three-point hitch sits among these fundamental interface standards that shaped their industries not through raw functionality, but through establishing universal connectivity. The system's influence persists in unexpected places, even when the literal three-point hitch isn't present. Front-end loader attachment systems on construction equipment often use similar geometry: triangular mounting, multiple pivot points, hydraulic control. These aren't three-point hitches technically, but they're intellectual descendants, applying Ferguson's principles to different machines. Even theoretical work on autonomous agricultural robots reference Ferguson's concepts. How should a robotic implement vehicle sense soil resistance and adjust operating depth? The most efficient approach remains something recognizable as Ferguson's draft control principle: sense resistance through the implement, adjust position to maintain target force, transfer load into downward pressure at drive wheels. Current tractor manufacturers continue refining hydraulic systems, electronic controls, and implement interfaces, but they're refining details around a central invention that proved so fundamentally correct that successive engineers spend their careers optimizing his solution rather than replacing it. This durability stems from Ferguson's approach to engineering. He didn't design a product. He designed a system that addressed fundamental physical relationships. The product, the actual hardware, was simply an implementation of those relationships. Superior implementations can and have been developed, but they succeed by better executing Ferguson's principles rather than replacing them. Standing in a modern tractor dealership surrounded by machines bristling with GPS antennas, computer displays, and electronic sensors, it's easy to miss the mechanical simplicity at their core. Lower those machines' rear hitches, and you'll see Ferguson's geometry: 3 connection points forming a triangle, lower arms pivoting at the rear axle, upper link sensing draft. The assembly might be controlled electronically rather than mechanically. The hydraulics might be load sensing and digitally modulated. The implement might transmit its specifications via isobus protocol. But the geometry is unchanged from what Harry Ferguson sketched in his notebook a century ago. That persistence, that fundamental correctness that transcends technological change, defines genuine engineering innovation. Ferguson didn't invent a better implement connector. He discovered the correct way to connect implements to tractors, a solution so aligned with physical reality that every improvement since has been refinement rather than replacement. Modern farmers operating autonomous tractors guided by satellites and controlled by artificial intelligence rely on a mechanical linkage geometry designed by a man who built his first airplane from scratch in 1909. That's the genius of Ferguson's three-point hitch. Not that it was sophisticated for its era, but that it remains correct for ours.